Hello, and welcome to the Chapter 6 video or videos, depending on how long this goes. I hope you've enjoyed the Chapter 5 videos. This is not trivial stuff. It gets much more complicated when we're balancing equations and going from grams to moles to molecules. And the nice thing about Chapter 6 is, if there's any nice things, is that it's a continuation of Chapter 5. It is extending the idea of how the world must be conserved to include energy, and we know this intuitively. For instance, you well know that like you get 25 miles to the gallon. So what does that mean? That means that every time you have this fixed amount of fuel, you get a fixed amount of work out of it. There is a certain amount of energy stored in that gallon of petrol. You know how your body how long you can go with a bran muffin, right? Before you get hungry again. There's a fixed amount of fuel, there's a fixed amount of energy. So what I'm going to argue and tell you is that heat is part of a balanced equation. So we can argue that that let's say I burn 1 mole of propane, there is a fixed amount of energy that is produced by that combustion reaction. And it's always the same, it's fixed. In fact, you can go right now on Wikipedia and they'll tell you the boiling point of propane and the melting point, though it's very low. And they'll tell you, all kinds of physical constants, and they'll tell you how much heat you get from burning, from the combustion of 1 mole of propane. So it's a fixed amount. And so we're going to evaluate that as well as we can, as well as chemists can. And I know this sounds like physics. In a sense, no chemistry is occurring, but it's important to understand heat and the flow of heat and the effects on kinetics, meaning whether a reaction is slow or fast and whether a reaction will occur or not. For this video, I'm going to take a leap here, and I'm going to see if using PowerPoint helps this video. So much of the rest of this video, you'll be pleased to hear, won't feature my face. So I'm going to show you some critical slides from the PowerPoint you already have. So here we are. In Chapter 5, we talked about some straightforward ideas. And what we see here is the combustion of propane. And when propane burns, because it's combustion, it must require oxygen and produce carbon dioxide and water. Guaranteed, I'll ask that on a quiz. And when it does, all the oxygens on the left of the arrow and on the right must be the same. And when it does, all the carbon on the left and on the right must be the same. You see here, there are 3 carbons on both sides. And that's true for moles. And it's true that this is a ratio, meaning if 1 mole of propane produces 3 moles of carbon dioxide, 3 moles of propane produce 9, which is 3 times 3 moles of carbon dioxide. If I know I produced 16 moles of water, well, 16 is 4 times the 4 in the balanced equation. Okay, everything is multiplied by 4. If I produced 16 moles of water, I must have had 4 moles of propane. And I need 20 moles, which is 4 times 5, of oxygen. And we know this is true for moles, but it's not true for grams because all the atoms weigh differently. So we need to understand molar masses, grams to moles, moles to grams. And there are some good videos on Brightspace related to this, and I'll put on more as I find them. Um, but what is true about mass is that all the mass on the beginning, the left side of the arrow, before the reaction, and the mass at the end must add up to the same thing. You can check this equation to see that the mass on the left and on the right add up the same. So that's where we were. And what we're going to do in chapter 6 is add in the idea of heat and light and energy, basically. And in this case, and in all combustion reactions, whether it's propane or the octane in your car or the bran muffin in your stomach, those are all combustion reactions, things on fire, right? And when things are on fire, they give off heat. So in all cases, combustion gives off heat. Now, in most cases, we don't know whether a reaction absorbs heat or gives off heat. And I won't ask you, does ammonia, the production of ammonia, gain heat or lose heat? And often I don't know the answer, and it doesn't matter. Just the ability to evaluate what you see in front of you. So if we're going to talk about heat, let's talk about some units. So what you see here is a calorimeter, a calorie meter, a calorimeter. Calorimetry is the tool by which we study energy absorbed or given off, and most often the energy of combustion. So what you do is you put in this machine, which is heavily insulated, and it's insulated outside, and then there's a water jacket, and then inside that water is a sealed container with some carbon fuel and oxygen. And if you light it and it's all combusted, it's hard to understand how much heat is given off by that combustion, but we know that all the heat is absorbed by the water, and we can easily study that with that thermometer you see up at the top right there. So a calorimeter is a calorie meter. Now, you probably think of calories in terms of food, and that's reasonable. That's what we think of when we think of calories, but it's not actually a unit of food. It's a unit of energy, of heat energy. What a calorie is the amount of energy that's required to raise 1 gram of water by 1 degree. And we have two famous units of heat energy, calories and joules. And basically, they're the same, only one's 4.184 times as much. You've been doing this in your homework. So joules and calories, both units of energy. And we'll often, going forward, describe energy in terms of kilojoules per mole. So how much energy is given off by the combustion of 1 mole of propane? Well, it's hypothetically 500 kilojoules per mole, right? Because you want to know how much per unit of mole. And you're thinking, wait a minute, calories and is only 1 gram of water, 1 degree? But when we talk about food, when we talk about, how much energy is stored in a Snickers bar, we don't actually talk about small c calories. We talk about large c calories. You see it, calories here. And when we talk about large c calories, that's actually a bit of a lie from the food industry. Large capital C calories means 1,000 calories. It actually is a kcal, which is 4.184 kilojoules. Um, and what, since we're here, let's talk about the energy in food. Um, all living things are pretty much composed of three things. They're composed of protein, almost entirely protein, but there are carbohydrates, and not just sugar you use for energy, but there are signaling sugars and all kinds of sugars for all kinds of purposes in your body. Carbohydrate is a long string of these single sugars. And there is, of course, fats and oils. We need fat. I know we don't like fat, but we need it for our diet. Too little fat, we'd have no ability to burn it as energy. Fat is a storage system for food energy. Fat is potential energy, stored energy. And when we burn it, we get lots of energy. The downside, of course, being that if we don't burn it, need a lot of energy to burn it. It's a lot of stored energy. How much? Well, it's more than twice as much as carbohydrates and proteins. And it's kind of important to me that you know that biologically we're largely proteins with carbohydrates and fats. Fat and oil, by the way, mean the same thing. Oil is the liquid form of fat. Fat is the solid form of oil. Um, and why this matters to me is that you should know roughly what it is you eat. And you eat other living things. Everything you eat was alive at one point. And so it's also made of proteins, carbohydrates, and fats. And we're required, or food industry is required to put down how much fat, how much carbohydrate, and much protein is in each foodstuff. And you can see from this box at the lower left that there's 1.5 grams of fat. So you would say there's 1.5 times 9 calories per gram. That's 13.5 calories in that of fat. There is 8 grams of carbohydrates, lots of sugar. So that's 32 calories. And there is 3 grams of protein. So that's 4 times 3, 12. And if you add that up, you get roughly 60, which is what it says on the food stuff. So let's talk about energy, and let's talk about how we examine it in chemistry. So first of all, we need some terms. So here is an image of a reaction going on. First thing I want is some terms to be defined. You need to know the word enthalpy, which is the change in heat in a reaction. And it's nice because it's got a reasonable and logical unit for it. What you see there is capital H, heat, energy. And what you see before it is a triangle, which is the Greek capital letter delta. So delta H. And delta H, the delta, generally speaking, could be delta T for time or, whatever, changing anything. Delta means change of. So delta H is the change in heat of a chemical reaction. And when we study this, we call it enthalpy. It's about the heat of a reaction. And here we see our famous one example up at the top right, a combustion reaction. We know that when a carbon, fuel, and oxygen are reacted, they give off heat, they catch on fire in one form or another, and they produce carbon dioxide, water, and energy. But not all reactions produce energy. Some reactions require energy, right? So if I were to say that the most famous example of a reaction that gives off heat is, well, eating an apple or running your car, the most famous way of thinking about the other type of reaction, a reaction that requires heat, is cooking. Cooking is chemistry. In the oven or on your stovetop, what occurs is chemistry. What occurs is heat being added to reactants, starting material, and those reactants undergoing chemical changes that you desire. So what we have at the majority of the slide is two views of reactions. And I want you to note that the axes really matter. So the y-axis, the up and down axis, is the stored energy, the energy of this reaction. You can call it energy or potential energy. You should include units. The units are kilojoules, or more accurately, kilojoules per mole. And the x-axis is kind of enigmatic because I've seen like 5 different answers to what the x-axis should be. Including time. The textbook sometimes refers to it as time, and that's a unfortunate choice because this is not based on time. Just because a reaction absorbs heat or gives off heat doesn't tell you whether it takes 1 second for this reaction to occur or it takes place over 100 years, right? We don't know. But when you label a x-axis, you'll call it just the reaction or the reaction pathway. And of course, I would even accept time. But what's most important to see here when you see this reaction, when you look at the left one, there is a certain amount of energy stored in the reactants. I'm moving my cursor over. See right there, reactants. There's a certain amount of energy stored in that material, and then a reaction occurs. And then at the end of it, when you have products, there's only this much energy. In other words, for the reaction, not for the surroundings, but for the system, for that reaction, the energy's been lost. This is possibly a combustion reaction. Energy has been lost from the starting material. It's gone down. It has changed the amount of heat in that material. It's gone down. It's negative, right? Let's say hypothetically that it started at 500 kilojoules and it ended at 100 kilojoules. It lost 400 kilojoules. It's a delta H of minus 400 kilojoules because heat left. And for the reactants, that's a loss of heat. So when you look at a reaction that is graphically like the one on the left, what you're talking about is a reaction where heat is lost from the system and given off, therefore, to the surroundings. This is an exiting heat reaction. And the word we use for exiting heat is based on 2 Greek words, exo for exiting and thermo, heat. So exiting heat, exothermic. When heat is given off, if you're holding a beaker and a reaction's taking place in that beaker and your hand's getting hot, it's exothermic. Heat is given off. Now, not all reactions, obviously, are like that. Some reactions don't do anything until you put heat in. So in certain reactions, there is very little heat in the system, in the reactants. But at the end, there's a lot more heat, right? Raw egg, boiled egg, unbaked cake, cake that has been baked. energy put in. And you see that on the right. You see that the reactants are low in energy down here, and at the end, they're higher in energy. Look, heat is taken in, it's absorbed. The delta H is positive, meaning it's gained energy, right? So you'll notice something else about this graph on the right, and that is that there's this weird little hump. And it turns out that the graph on the right is more accurate about chemical reactions than the graph on the left. And the reason is, back to me, the reason is that energy is always required for a reaction to go on. When you were in, I don't know, third grade, you were told about the fire triangle. Right? So fuel and oxygen and heat, they're all part of any chemical reaction. And oxygen and fuel are straightforward, but heat is more enigmatic. What it hinted at, I'm going to talk about directly today. What it hinted at is that every reaction needs a push. So even propane, without a spark, won't burn, right? Paper won't burn without a spark. Even exothermic reactions that will go on forever need energy to start any reaction. And endothermic reactions definitely need heat to start it. Every reaction needs some starter. And sometimes that heat is very small, right? Any spark near propane will set off a chain reaction of propane that burns the whole house down, right? But some reactions need lots of input heat. There's a famous analogy chemistry teachers use, which is to describe a reaction as being like a bicyclist trying to get to a village, right? Whether the village is, here's the village at the end. There's my high resolution bicyclist. He's trying to get to that village, and that village, those houses are on a higher plateau. So this village has an energy requirement of that bicyclist. But, and that was supposed to be a delta H right there. But it's not enough to talk about the bicyclist as having to go from this energy level to this energy level at the end, from here up to here. That's not all that bicyclist has to do. That bicyclist has to get over that hump of energy. And that hump is that heat. See that right there? That's the heat of the reaction, that hump. And so what's happening is every reaction needs some activation, something to push it forward. And that activation is called, fortunately for us, the energy of activation. And you often say E sub A. And it's sometimes a capital A and sometimes it's a small a, but it's the energy of activation. And that's what you see here. Notice that this reaction needs, the poor bicyclist has to get up that mountain to get to the product. And it should be said, the higher the hill, the slower the reaction as a general idea. And it makes sense. If you need lots of energy to get a reaction to go, then it takes more energy, less molecules will have that amount of energy, the reaction's slower. And not just endothermic, heat absorbed reactions require heat. Even exothermic reactions, right? So there's the heat of propane. They too, the bicyclist, he requires heat, right? So there's energy required from reactant to the top of that hill is the energy required in this reaction. And then the difference between where he started, or she, and where she finished is delta H, right? So that distance is the change of heat in this reaction. All right. So what do we know? Reactions either need heat or give off heat. So there's a reaction, X plus Y makes Z, and heat. If heat is a product, it is exothermic. You can see the heat going away, right? There's a heat leaving. So there was energy here, and now Z doesn't have it anymore. It's left. It's exothermic, which means that the other way to write this is that delta H is negative. Let's say it's negative 300 kilojoules per mole. Right? Exiting heat, negative. Right? And if heat was on this side of the equation, X plus Y plus heat, that means one of the starting materials, the reactants, is heat. That's endothermic. The reaction needs heat. All right. So on that bombshell, let's stop this first video and we'll make a second one that will finish the topics of heat and energy, and we'll talk about equilibrium, which is the end topic, strangely, in chapter 6. So thank you, and please watch both videos so that we can do a quiz successfully and do exams successfully and enjoy this course. Thanks for your time.